For this one, writing Lewis dot structures, there's a lot of different types of molecules. They all fall into certain categories, and there's, I'd say, somewhere between 15 and 20 different categories. But they all work, when you're trying to draw their Lewis structures, they all follow the same kind of procedure. So I'm going to do out, let's see, 2, 4, 6, 8, 10, or 9 different types. And just when you're doing these out, just pay attention to the procedure. You'll see that it's the same each time. There's a few little things that we have to keep track of as we go, little differences and exceptions. But let's start with CF4, tetrafluoro methane. So first thing is they say to calculate the number of valence electrons. Well, carbon is in group 4A, so there are 4 valence electrons for carbon. Fluorine is in group 7A, so that's 7 valence electrons, and there's 4 of them. So that is 32. So if you know the group they're in, and you have the periodic table which will tell you, if they're in group 1A, then it's 1. Group 2A, 2 valence electrons. Group 3A, 3 valence electrons. So that shouldn't be too much of a problem with the periodic table, and after a while you'll know these offhand. So the second thing is to draw a structure with the central atom connected to the outer atoms, and that's one thing that you have to decide, is which is the central atom. Well, usually central atom is shown first. Usually it's the only one, and then it's the less electronegative. Since fluorine is the most electronegative element, anything connected to it is going to be less electronegative. Fluorine can only form one bond, and so it's always on the outside. So we got a ton of things telling us carbon is the central atom here. Then you complete the octet for the outer atoms, assuming that they need an octet. There is one exception that we'll talk about. Once you've completed the octet of the outer atoms, then if there's any remaining electrons, you put them on the central atom. Well, let's see. Each fluorine now has 8. 2, 4, 6 that we added, and then 2 that are connecting it to the carbon. And when I drew out that structure, I drew a single bond from the central atom to the outer atoms, because there has to be at least one bond. If it's a molecule, there has to be one. So that's why I did that initially. So we have 8, 16, 24, 32. They all have their octet. The central atom has its octet. Everybody's happy. So without the circles, that would be the structure. You don't have to circle. I'm just showing that they fulfill the octet. Now we go directly into an exception, because the ones that follow the rules, they're actually, you do a few of them, you got it made in the shade. There's no problems. It's the exceptions that get the students. So I'll do some that are exceptions, some that are ones that follow the octet rule. We're always trying to get 8 electrons around the atoms, unless otherwise stated. Now, beryllium is an exception. Beryllium is in group 2, so 2 electrons. Fluorine is in group 7. And the reason fluorine comes up over and over, because it only forms one bond. And so there's no way of making a mistake with the exceptions if you keep that in mind. So we fulfill the octet. Now we have 8 electrons, 16 electrons. There's no more. If there were any more, we could put them on the central atom. We don't have any more. So we're done. And beryllium doesn't have its octet, but it doesn't need it. It's one of the exceptions. And even if you forgot that rule, if you remember that fluorine only forms one bond, it's always on the outside, you'd have to stop and say, well, okay, wait a minute, there's nothing left. Okay, this must be an exception, even if you've forgotten. So a second exception is boron. So I'm going to do a lot of these exceptions. Now, they say to find the valence electrons first. I usually just draw this out, because we know that this is the central atom, because fluorine has to be on the outside. We know there's at least a single bond to each. So that's where I start before I do anything else. But they say to find the valence electrons. Boron is in group 3A, so it has 3 electrons. Fluorine is in group 7. There's 3 of them. So that's a total of 21, so 24 total. Complete the octet on the outer atoms. And that's all 24. 8, 16, 24. You should get used to you should get used to seeing the multiples of 8 for these electrons. It won't always happen, but when you see that, usually it means that the outer atoms get all their electrons, and then there's none left for the inner, for the central atom. Fluorine only forms single bonds, so this is another exception. Boron only gets 6 electrons. It's small, that's what it can accept. Beryllium and boron will explain much more in depth the next chapter why this bonding scheme is what it is, why they break the octet rule. I'm going to make this ammonia because I want to point out something. Oops. So nitrogen, first thing first, I just draw out the structure. Nitrogen has 5 electrons. Hydrogen is from group 1A, so it gets 1. 8 electrons total. Now here is another exception. Hydrogen only gets 2 electrons. If you do that, it fills up its 1s2 orbital, and then there's nothing further that it wants to do. You're not going to add 6 more electrons to a tiny atom like hydrogen, so it's done. So once even though it doesn't fulfill its octet rule, or doesn't fulfill its octet, it has all the electrons it needs. So 2, 4, 6. There's 8 that we have to use, so the 2 that are left go on the central atom. Now that's the first time we had to do that. That's the rule. Once the outer atoms are set, then you put the rest of the electrons on the central atom. Alright, here's another exception to the octet rule, because there's lots of them. You can see that it's an exception because we have 5 fluorines. Each one is going to have to bond to the phosphorus with 2 electrons, so that's 10 electrons. So we can already see that it breaks the octet rule by going the opposite way from boron and beryllium that has too many now. So a phosphorus has 5 electrons, a fluorine has 7. 7 times 5 is 35 plus 5, that's 40 electrons. Now here, instead of writing out the 2 electrons, this bond represents 2 electrons, and the line is supposed to be a bond, but to save ourselves some trouble and some time, we can just put the lines around, and each one represents 2 electrons. And as long as you're careful not to let this line get anywhere near a bond, then it should be fine. So we have 8, 16, 24, 32, 40, so we're done. This is the full form of it. Now notice we have 5 bonding pairs and 0 lone pairs around the central atom. That's for phosphorus. Now what about this one? Sulfur, well, we're going to have sulfur has 6 electrons. The fluorine, there's 7 times, I should say 4 times 7. So that's 28, so that's 34. You can see that's not quite a multiple of 8, so it looks like we're going to have extra electrons. And when I say these things like that, if you don't see it, that's fine. You will if you keep going. See, so we know we have 32. We have 2 left over. So if you keep going and working on these, you'll start to see these kinds of things that you're looking for. When this doesn't come up to be a multiple of 8, then that generally means that we're going to have some electrons left over to put on the central atom. We have 2 left over, so it goes here. Notice there are still 5 pairs of electrons. There are 5 here around the central atom, 5 bonding, 0 lone pairs. But here we have 4 bonding pairs and 1 lone pair. I'll just abbreviate. But still 5 total. 1, 2, 3, 4, 5. So we'll see in the next chapter that these 2 structures, they have the geometry of the electron pairs, how they separate out in space is the same, but they have a different shape when you just look at the atoms. But not important right now, but just notice that they are related through the number of pairs of electrons on the central atom. Alright, let's look at this. We have boron pentafluoride. The larger halogens can form more than 1 bond. So fluorine doesn't, but bromine does. I just draw this out first. Now they're all from group 7, so there's 6 times 7, so that's 42 electrons. if we complete the octets for fluorine, and fluorine will always get its octet, and it only forms a single bond, that's 40. 1, 2, 3, 4, 5 times 8. So 2 are left over. There we go. So we have 5 bonding and 1 lone pair for the bromine. Alright, now we get into something that, 2 things are going on here. First, it's a polyatomic ion, and second, it'll have resonance structures. But let's just draw it out like we were just trying to construct a molecule. So we have nitrogen is 5 from group 5A, so 5 electrons, 3 times 6 for the oxygen, and then 1 for the charge. So this is for the nitrogen, this is for the oxygen, and 1 for the charge. If it was -2, there'd be a 2 here. If it was +1, then we'd have to take away 1 of the electrons. So the valence electrons are involved in bonding, and they also provide the charge on the polyatomic ion. So this is 18, 23, 24, and we get to a multiple of 8. So looks good. We put these guys on here, as we should. That's 24 electrons. But the nitrogen doesn't have its complete octet. So what that tells us is one of these, what we thought was a lone pair, was actually a bonding pair. You also put it in square brackets with the negative sign to indicate that it's a polyatomic ion, and put the charge out there where we can see it. So this scribbled out means that that lone pair is no longer there. But notice that the double bond could go between the nitrogen and this oxygen, or this one. These are resonance structures. What that means is that that pair of electrons is allowed to be between any of the 3 oxygens. So we want to draw all 3 so that we can make sure that it's understood that we haven't allowed one of the oxygens to be preferred. All of them are allowed, so you want to draw them all. So if you have, this will come up with a lot of these polyatomic ions. If there's more than one structure that can be drawn that's identical except in the position of that double bond, then you have to show them. Also, when the central atom is not beryllium or boron, you have to make sure it has an octet, and the way to do that is to create a double or even a triple bond. Okay, so let's look at sulfuric acid. Now, I'm showing this because it may not be obvious how to proceed, but in oxo acid, the hydrogens are attached to an oxygen. There's only 2 hydrogens, so there's only 2 oxygens involved, and then the other oxygens are just connected to the central atom. So there's 2 electrons for the hydrogen, 6 for the sulfur, and then 6 times 4, 24 for the oxygen. So this gets a little trickier, because we still have a central atom, but then we have these other guys attached on the ends. But try to complete the octet. Did a poor job with this bond, sorry about that. Everybody has their octet. Now, that looks fine as far as we go, but we're going to learn that there is this structure is not quite correct, but we'll look at the formal charges. But at this point, with the knowledge that you have, that is fine. C2H4. Now, when you have more than one atom of the same kind on the left, that means that they're bonded together in this way. And then the hydrogens, we know they can only form one bond. They only have 2 electrons around them, and that's due to the bond. So there's nothing further to be done here. We have with the hydrogens, and we want to have them symmetrical. So we have 4 electrons, and then we have 8 total for the carbons, so that's 12. So 2, 4, 6, 8, 10 are done. The last one, well, we could either put it on this carbon or this carbon, but that wouldn't be symmetric. It must be between them. Now the carbon has its octet, and carbon will always get its octet. Same for nitrogen, always gets its octet. Same for oxygen. These smaller atoms insist on having their octets. So if you see a carbon in there, you know that you're going. If you don't initially see 4 bonds to it or 4 pairs of electrons around it, it's going to need it. And then the last one that we're going to do is this, where it's we've taken away 2 of the hydrogens. We did C2H4 before, now it's C2H2. Carbons have to be like that, and then where do the hydrogens go? Maybe both of them go on one carbon, but they tend to be symmetrical. So we have 4, carbon is in group 4A, so that's 8 total for the carbon. We have 10 for total. We have 8 for the carbon, 2 for the hydrogens, and 10 total. 2, 4, 6, 8, 10. That's a possibility, except that the carbon doesn't have its full octet. So we put that there, then it's not symmetrical, so that would be the only possibility, where everybody has their octet. The carbons each have their octet. And that reminds me one more, since we have a little time here. CO2, we have this, and we have 4 electrons for the carbons, 12 for the oxygen, 16 total. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That can't be right because the carbon doesn't have its octet. It's not one of the exceptions. So we can do one of 2 things. We can bring this carbon over. We can bring a lone pair in from here and from here. Now the octet rule is followed. 8, 8, and 8. But there seems to be something off. It seems wrong. What if instead we brought a lone pair from here? Then we end up with something that looks much more symmetrical. And if you had to look at these 2 molecules and determine which one is the most stable, or the one that we'd expect to see, you'd pick this one most likely because it seems more symmetrical than this one. And you'd be right. Now, if we didn't go any further with the formal, what we'll do next is talk about formal charges. Our rules would not be able to pick between these. You'd probably pick this one just because it looks better. It has that symmetry to it. But we'll talk about why this one doesn't happen. Now, on the exam, once you have studied the whole chapter, you'll know about formal charges. So you shouldn't be able to. You shouldn't use this one. It will be this one. So in a later video, you'll see the distinction between these 2.